What is the partial summation formula? So you see, this is also called in the book summation by parts. And it reminds, you see, when we take the integration by parts, basically we are undoing the derivative of a product. Okay, so it's about products. Okay, so in this case, instead of having the integral, we are going to be working with a sum of a product, a and bn, and n will go from, let's do it in general, from p to q, between any two indices. Okay, and here, the way we do this, let's call an the sum from 0 all the way to n of the ak. We will say, if it comes to that, a of -1, we will define it as 0. Okay, and we will always, of course, we will say that p is lesser or equal than q. Okay, because otherwise this sum is empty. But it's good to put it as a disclaimer. So writing it like this, the trick, and I prefer to actually write the computation because remembering the formula is too difficult, but remembering how to find it is actually quite straightforward. So what we are going to do here is to realize that an is equal to capital A n minus capital A n minus 1. Okay? This is the key trick, because then we can write an with this, in this fancy way, times bn, n equal p to q, and now it's just a manipulation. Let's continue over here. There is only one thing we can do right now, so it's distributing, right, n equal p to q, a n minus 1 bn. And here what I'm going to do, because I would like to have an in both sums, I'm going to change, and I'm going to call n minus 1 equal, let's call it, am I using m? No. So let's call it m. Okay, so then this is the sum from n equal p to q, a n bn minus the sum of a m b m plus 1. And then when n equals p, m is p minus 1. And then when n equals q, m is q minus 1. So this is it. And now we should be able to I mean, we have an on both of them, so we could factor that out. But the problem is that we have different endpoints for the sum. So we need to fix that. So the way we fix that, we just add what is missing. Let's sum from m equal p to q, a m b m plus 1. And then notice here, I need to subtract a p minus 1 bp, okay, because that's the extra. Actually, there is one extra because m starts earlier. It starts at p minus 1, okay? So that one stays there, but then here I'm putting the sum all the way to q, and q was not there before. So because I'm subtracting, I need to add to compensate. So this is plus aq bq plus 1. And I think we got all the ingredients. Here now, because the index doesn't matter, so I'm going to call it n instead of m. And we can factor things out. So an times bn minus bn plus 1 minus ap minus 1 bp plus aq bq plus 1. And this is the formula for summation by parts. Okay, so let's copy paste and let's dignify this formula. So this is the sum from n equal p to q of an bn. We write it like this. And this is a useful trick when we need to deal with series that are a product of two sequences. Okay, the general term is a product of two sequences. But you see, in my opinion, it's easier to just do the computation on the spot. So let's see some applications. So the first one, here we are going to suppose three things. So the partial sums an of the sequence, the series am, so m from 0 to n, these are a bounded sequence. A bounded, let's just write bounded sequence. The second thing is that the sequence B is decreasing. And then the third one is that the limit of this Bn is 0. Okay, so it's decreasing to 0. Sometimes you will see this written as Bn decreasing to 0, but this doesn't capture the fact that it's monotonically decreasing. Okay, you see that its term is bigger than the next. So then the sum of a and bn converges. And for the proof of this, we are going to use the partial summation formula. So let me copy paste. Let's keep it here. How do we show this? So what we are going to do, the general strategy to show that it converges, is to show that the partial sums of this a and bn series, those partial sums form a Cauchy sequence. So we are going to see that when we look from n equal p to q, with this p and q large enough but arbitrary, the result is going to be smaller than epsilon for epsilon fixed. That's the general strategy. Okay, but for that first we need to figure out how to estimate this sum of a and bn. So let's do first things first. First thing, the estimate. This is just the partial summation formula. Okay. And here, one thing I want to note is that bn minus bn plus 1, because the sequence is decreasing, is going to be non-negative. That's going to be important. Here, we are not going to apply the triangular inequality because we will lose important information. Instead, what we are going to use is that an is bounded, which means that an is less or equal in modulus than some constant m. Okay, so we can actually bound every am that appears here by m. So we have n equal p to q, bn minus bn plus 1 minus bp plus bq plus 1. Actually, we can even put plus here. And then we realize, when we look at this expression, we realize it's a telescopic sum. What does it mean, telescopic? So let's just write it down, see what happens. BP minus BP plus 1 plus BP plus 1 minus BP plus 2 plus BP plus 2 minus BP plus 3, and so on, until BQ minus BQ plus 1. And here, if we start canceling, you see that everything appears adding and subtracting. So we actually can cancel every term except for the first and the last. So this is the sense in which this is telescopic, because you expand it and then it contracts to just two terms. So the whole thing that we have in this big sum is BP minus BQ plus 1 plus BP plus BQ plus 1, magic. And then we get to BPM. And we are almost set, because remember I said we needed to estimate, right? So here we have our estimate. This is from n equal P to Q, AN, BN, lesser or equal than 2 BP M. And here I want this to be lesser or equal than epsilon. Okay, so for that, I need to guarantee that this BP is not going to give me trouble. But now here, notice something, the BP is decreasing. So BP is lesser or equal than Bn for all P bigger or equal than N, any N we pick. Okay, so here actually I can just write to Bn M and choose N such that Bn lesser or equal than epsilon over 2m. Okay, so if you do this, then you can guarantee then the sum from P to Q, Am, Bn is lesser or equal than epsilon for all PQ bigger or equal than N. Remember, Q is bigger than P anyway. And this is what we needed to show that the series is Cauchy. Criterion. So the series is convergent. And that's it. Okay, notice here, instead of doing the usual way, the way it's written in the book, I have decided to show you why in the beginning of the proof, the book will say you need to take m and then epsilon divided by 2m and all that. The reason is because when you arrive to this point, you just estimate. How can you get all these things that you got here? How can you force them to be less or equal than epsilon? Okay, so that's the way you actually think about analysis. One consequence of this theorem is the series that we were discussing in the previous video. Okay, we said that this one was converged for every z with modulus 1 as long as z was different from 1 itself. Okay. I mean, this is obvious because if I put z equal to 1, then I have the harmonic series. Okay, so that one, no hope. What is a bit surprising, to me at least, is that all other values would work. Now, here we are going to take an, which is z to the power n, and bn, which is 1 over n. Remember, bn needs to be decreasing with this is, and we need bn that converges to 0, which is also true in this case. So we are under the hypothesis of the theorem. Well, wait, there is one more. We need to check that an, which is the sum of the am from m equal 0 to n, forms a bounded sequence. Okay, so for that we need to check. So let's get to it. So this is the sum from m equals 0 to n, sorry, zn. On this one, we can actually use the formula for the sum. This is 1 minus zn plus 1 divided by 1 minus z. And then here, this is 1 plus z to the n plus 1 divided by modulus of 1 minus z. And because z is equal to 1, we get 2 divided by 1 minus z. And that's it. Here, notice it's very important that z is different from 1. Okay, because if it were, this this wouldn't work. Okay. All right. So then the hypotheses are satisfied. And then what we have is that the sum from 1 to infinity of a and bn, which is my power series, converges. Okay, which is what we wanted to show. In the book, you can find this I did here. You can find it in a more general format. Okay, for different power series. So it's a general theorem, but I thought it was more clear if we would apply it to our actual example to see how it works. But you can see the general version in the book.